Extension of hierarchical decomposition, a modern approach to control system design. In complex chemical and energy production facilities, designing effective control systems requires more than loop by loop tuning. It demands a structured, scalable, and strategic framework. The hierarchical decomposition method addresses this by guiding control design from top level plant objectives down to unit level control loops, ensuring that economic goals, safety requirements, operability, and automation logic are aligned from the outset. Modern tools such as digital twins, process simulation platforms, APC suites, and AI augmented design environments have revitalized this methodology, enabling engineers to construct control architectures that are modular, transparent, and performance optimized across all operational layers. Why hierarchical decomposition matters today. Traditional control design often begins too late, once the process flow sheet is already fixed, leaving limited room to optimize control structure or accommodate loop interactions. Hierarchical decomposition solves this by integrating control thinking into the earliest stages of process design, resulting in control structures that reflect strategic plant priorities, early identification of loop conflicts and controllability issues, easier incorporation of advanced process control APC or optimization, flexibility to adjust design before automation is locked in. In the age of Industry 4.0, this approach supports digital continuity between simulation, design, control, and operation. Modernized hierarchical framework. The method unfolds in sequential layers, each progressively adding control elements aligned with process structure and business goals. 1. Input-output structure, plant-level control. Objective, control total feed and product rates to define the plant's mass and economic boundaries. Modern tools and strategy. Define production targets using integrated scheduling or MES platforms. Install real-time reconciled flow meters with diagnostics. Use constraint-based controllers, APC, to maintain production while respecting equipment limits. Example loops: feed flow rate, product withdrawal or recycle balancing, energy input limits, e.g., steam or fuel rate. 2. Recycle structure, subsystem level control. Objective, like stabilize recycle flows and composition to avoid oscillations and bottlenecks. Modern tools and strategy. Apply relative gain array, RGA analysis and sensitivity studies to identify loop coupling. Use dynamic models to test flow or composition interactions. Consider soft sensors or inferential measurements to monitor internal flows. Example loops: recycle flow control, reflux or purge stream regulation, intermediate product quality control. 3. Functional subsystem structure, unit level control. Objective: implement control loops around reactors, separators, heat exchangers, and compressors, focusing on quality, safety, and efficiency. Modern tools and strategy. Apply APC or MPC to high-impact units, e.g. distillation columns, reformers. Use digital twins to simulate disturbances and validate control loop responses. Deploy machine learning for fault detection, auto-tuning, and process optimization. Example loops: reactor temperature and pressure, distillation overhead and bottoms composition, flash drum pressure and vapor liquid ratio, compressor anti-surge control. 4. Energy integration and control. Objective: optimize and stabilize energy flows across the plant. Modern tools and strategy. Integrate utility management systems, UMS, for steam, power, and cooling networks. Implement dynamic heat integration models and APC platforms. Design coordinated loops, e.g., column condenser reboiler links for pressure and composition control. Example loops: steam header pressure control, reboiler duty modulation, energy recovery exchanger bypass. 5. Inventory and pressure balancing, base level control. Objective: ensure material balances are maintained by adjusting one stream per control volume for level or pressure stability. Modern tools and strategy. Automate level tuning with self-optimizing algorithms. Use inventory buffers as dynamic load dampeners in APC coordination. Visualize mass balance deviation across units in real time. Example loops: vessel level control, column pressure via condenser duty, surge tank control, and buffer management. Modern advantages of hierarchical design: scalability, easy integration of new units or expansions without redesigning the entire control scheme. Model-driven flexibility, system response can be analyzed and validated at each level using first principles or data-driven models. Digital twin alignment, like digital control architecture, maps directly to the simulation hierarchy, supporting parallel development and faster commissioning. Strategic loop prioritization. High impact loops, e.g., affecting quality or profitability, are identified early and supported by advanced tools like MPC or inferential analyzers. Cross-disciplinary collaboration. Controls, process, and operations teams work together from the conceptual phase, aligning targets and decisions. Conclusion. The hierarchical decomposition approach, enhanced by modern digital tools, enables a proactive, structured, and economic-aware control system design methodology. It shifts control engineering from a reactive task to an integral design discipline, ensuring that process structures and control strategies evolve in parallel for optimal performance. In the digital era, this methodology lays the groundwork for autonomous, intelligent operations, where control systems not only respond to change, but continuously learn, optimize, and align with plant priorities. Three-phase separator control strategies, modernized approach for upstream oil and gas applications. Three-phase separators are essential in upstream oil and gas operations, where production fluids are separated into oil, water, and gas phases. These separators serve as the first major processing unit after the wellhead, managing slug flow, emulsion challenges, and composition variability while protecting downstream equipment. A well-designed control strategy is critical to maintaining safe, stable, and optimized separation under fluctuating reservoir and flowline conditions. In modern offshore and onshore production facilities, these separators are equipped with smart instrumentation, digital diagnostics, and advanced control algorithms integrated within distributed control systems (DCS), safety instrumented systems (SIS), and increasingly cloud-based analytics. Control objectives in upstream three-phase separation. A robust control system for a three-phase separator must ensure phase stability, maintain clear separation interfaces between oil, water, and gas for accurate routing and minimal cross-contamination, regulate pressure safely, stabilize vessel pressure to ensure proper separation and avoid overpressurization or gas blowby, balance inventory, maintain consistent liquid levels, oil and water, to avoid carryover or pump cavitation. Optimize flow and production, maximize throughput without compromising separator efficiency or safety. Modern degrees of freedom and control strategy. A typical three-phase separator has one feed stream, three product streams, gas, top or middle, and water, bottom. Two liquid-liquid and vapor-liquid interfaces. Degrees of freedom equals 4, streams, my two text interfaces, MathBF 2. This allows two strategic control loops, while the third outflow stream is used for inventory regulation through level control. Core control loops and strategies: gas pressure control, measured variable, separator pressure, manipulated variable, gas outlet valve or back pressure valve. Purpose: maintain steady state pressure for optimal phase separation and equipment protection. Oil level control. Upper liquid level, oil holdup. Manipulated variable, oil outlet valve. Purpose: prevent overfilling, carry over to gas or water systems, and maintain stable oil export conditions. Interface level control. Measured variable, oil-water interface level. Manipulated variable, water outlet valve. Purpose: ensure clean phase separation and protect downstream water treatment or disposal systems. Feed-forward override control. Measured variables. Rapid changes in feed flow, pressure, or level. Manipulated variables, outlet valves or feed choke. Purpose: prevent upset during slugs or surges by temporarily overriding normal control logic. Enhanced control features in modern systems. Smart instrumentation. Guided wave radar and capacitance probes with emulsion detection. Redundant transmitters with diagnostic alerts and calibration tracking. Real-time control optimization. PID and MPC algorithms optimize for slug detection and emulsion behavior. Coordination between separator, downstream pumps, and upstream choke valves. Digital twin integration. Simulation of transient behaviors, e.g., gas surges, emulsion slugs. Operator training and logic validation using dynamic models. Remote monitoring and predictive maintenance. Cloud-based dashboards for separator health, fluid levels, and valve diagnostics. Integration with CMMS for preventive maintenance based on wear, duty cycle, or vibration. Summary. In upstream oil and gas production, three-phase separators play a central role in stabilizing flow, enabling efficient separation, and protecting downstream systems. Their control strategies, anchored by pressure and dual-level control loops, must be precise, adaptive, and resilient. With only 2 active degrees of freedom and highly variable inlet conditions, separator control requires tight integration of smart sensors, advanced control logic, and predictive tools. When properly implemented, these systems enhance not just operational stability, but also production efficiency, safety, and equipment longevity, transforming a conventional separator into an intelligent processing asset. Slug catcher control strategies, modernized approach for upstream oil and gas applications. Slug catchers are critical assets in upstream oil and gas production systems, especially in multi-phase flow lines transporting unprocessed fluids from wellheads or subsea tiebacks. These large volume vessels are designed to buffer, absorb, and stabilize sudden influxes of gas and liquid slugs caused by terrain-induced flow regime changes, well startups, or pigging operations. Poorly controlled slugging can lead to compressor trips, flare overshoots, separator flooding, and process instability. Modern slug catcher control strategies go beyond passive surge protection. They employ advanced instrumentation, flow analytics, and coordinated valve logic to actively manage slugs, smooth downstream flow, and support digital field operations. Control objectives for slug catchers. A modern slug catcher control system must dampen liquid and gas flow variability caused by terrain or well dynamics, prevent downstream equipment trips by decoupling slugs from separators and compressors, optimize drainage of separated phases while preserving gas-liquid separation quality, enable pigging and upset handling without disrupting steady-state production. Typical slug catcher configuration. Slug catchers are either finger type, horizontal vessels in parallel, common in high-capacity gas fields, especially offshore or subsea tiebacks. Vessel type, large horizontal or vertical drums, used in compact or modular designs for onshore or smaller installations. The system typically includes inlet flow line, often multi-phase, gas outlet to flare, compressor, or gas processing, liquid outlet, oil condensate or produced water, to separators or storage, drain valves, level transmitters, and pressure sensors. Core control loops and strategies, inlet flow monitoring and slug detection, measured variables, inlet pressure, flow rate, density via Coriolis or DP meters. Purpose, identify the arrival of slugs or pig-induced surges using rate of change alarms or pattern recognition. Enhancements, use AI ML-based slug signature models and predictive flow analytics. Gas outlet pressure control, measured variable, slug catcher pressure, manipulated variable, gas outlet or back pressure valve. Purpose, maintain vessel pressure within safe limits and ensure smooth flow to compressors or flare. Features, integrated with compressor anti-surge control and flare system logic. Liquid level control, measured variable, liquid holdup level, typically using radar or ultrasonic sensors. Manipulated variable, liquid outlet valve to separator or tank. Purpose, control drainage rate and prevent overflow during high liquid slugs. Enhancements, valve characterizations and surge-tolerant PID tuning to avoid overshoot during slug discharge. Interface control for two-phase drainage systems, measured variable, water-oil interface if separated liquids are present, manipulated variable, independent water and oil outlet valves. Purpose, maintain clean phase separation in finger-type systems with internal settling. Slug buffer management and drain sequencing, logic-based control, valve sequencing for timed or level-triggered draining from each finger. Purpose, stagger slug release into downstream system to avoid overloading separators or compressors. Modern enhancements, PLC DCS logic with FERT interlock drainage timing. Adaptive logic that delays drainage based on downstream readiness. Integration with separator level and pressure conditions. Advanced enhancements in modern systems. Slug anticipation via line pack models. Use upstream pressure, temperature, and flow modeling to predict liquid holdup and pre-trigger buffering or drainage. Model-based predictive control, MPC, to throttle choke or flare valves in anticipation. Pigging coordination and override logic. Override liquid outlet valves during pigging to absorb incoming surges. Trigger temporary ramping of flare valve or compressor load shedding logic. Digital monitoring and visualization. Real-time dashboards display finger utilization, slug frequency and volume trends, drainage response time, remaining buffer capacity. Remote supervision and edge control. Remote control logic modules via RTU or edge gateway manage remote slug catchers in unmanned well pads or satellite tiebacks. Secure connectivity supports override, trip, and failsafe actions from central control rooms. Typical control scheme summary, bulleted. Gas pressure control. Controls slug catcher vessel pressure using gas outlet valve. Ensures safe delivery to flare or compressors. Liquid level control. Regulates liquid drainage based on level transmitter readings. Prevents overflow or carryover into gas system. Slug detection and surge buffer logic. Monitors flow patterns and pressure spikes. Activates timed or conditional drainage strategies. Drain valve sequencing. Sequentially empties fingers or surge volumes to avoid downstream upsets. Maybe manual, time-based, or automated based on conditions. Pigging integration. Overrides normal control loops to accommodate pig arrival. Triggers pre-drain or buffer hold logic as necessary. Summary. Slug catchers are more than mechanical buffers. They are active control nodes in the upstream production network. Modern control strategies enable them to absorb transient slugs, stabilize downstream operations, and adapt dynamically to changing flow conditions. With the integration of smart sensors, adaptive logic, predictive models, and digital interfaces, slug catcher systems are now equipped to prevent equipment trips, improve flow assurance, support remote and autonomous operation. By treating slug catchers as control assets rather than just vessels, operators enhance uptime, safety, and throughput shared in even the most challenging multi-phase production environments. Outline of procedure. Hierarchical control system design in the modern plant. The hierarchical design of control systems follows a structured, layered methodology that mirrors the process design itself, from high-level material balances to detailed equipment-level regulation. This approach allows engineers to place control loops progressively, with each stage building on a simplified flow sheet, enabling clarity, flexibility, and alignment with plant economics and operability goals. In modern control environments, this procedure is supported by dynamic process simulation, integrated control design platforms, real-time data analytics, and digital twins, which accelerate the decision-making process and ensure system robustness before physical deployment. Step 1. Input-output structure. Define plant-wide strategic control. Objective. Control the material and energy boundaries of the plant, specifically feed inputs, product outputs, and utility consumption. Activities. Identify feed and product streams in the simplified flow sheet. Determine primary disturbances, e.g., feed variability, product demand, and their timescales. Assign control loops for total feed rate, key product withdrawal, major energy inputs, e.g., fuel, steam, power. Modern tools, real-time performance dashboards linked to DCS ERP systems, APC supervisory set points linked to production planning, simulation of throughput sensitivity using dynamic models. Step 2. Recycle structure. Stabilize internal circulation and intermediate inventories. Objective. Prevent instability caused by internal feedback paths in recycle loops. Maintain consistent composition and flow within subsystems. Activities. Add recycle streams to the process representation. Analyze process controllability using relative gain array, RGA, or dynamic sensitivity tools. Determine which loops can independently regulate their targets without destabilizing neighbors. Modern tools, control structure analysis software, e.g. Aspen DMC+, MATLAB RGA tools. Live data extraction from plant historians to model dynamic interactions, recycle loop optimization in digital twins. Step 3. Functional subsystem structure. Configure unit-level control. Objective. Place control loops on reactors, separators, exchangers, compressors, and other key units to meet specific functional and economic objectives. Activities. For each unit, define key process goals: temperature, composition, conversion, pressure. Apply standard control strategies or model-based logic based on the unit operation type. Assign manipulated variables based on response speed, interaction risk, and economic impact. Modern tools, equipment-specific control templates in modern DCS or simulation libraries, real-time online models to guide control pairings, APC models that span entire functional subsystems. Step 4. Energy integration. Optimize thermal and utility control. Objective. Ensure efficient use of utilities and integrated thermal systems while maintaining pressure, temperature, and balance. Activities. Add heat exchangers, steam networks, and utility interconnections. Replace standalone utility control loops with coordinated APC or optimization logic. Evaluate bypass strategies for heat integration trade-offs. Modern tools, energy management systems, EMS, utility optimizers embedded in APC layers, integration with site-wide steam and condensate balance models. Step 5. Inventory regulation, balance mass, and maintain levels. Objective. Ensure material balance in each subsystem by using one stream, typically the last unconstrained stream, to regulate inventory. Activities. For each vessel, identify inflows and outflows. Use strategic control for N-1 flows and reserve the final stream for level or pressure control. Prefer level loops with minimal process interaction, e.g. product side control. Modern tools, self-tuning PID controllers with level prioritization logic, adaptive tuning for surge tanks and buffer vessels, DCS integrated inventory dashboards with predictive alerts. Guidelines for implementation at each stage. Start simple. Begin with the highest level flow sheet and add detail progressively. Question every stream. What is its role? Can it be manipulated? Does it require control? Avoid premature detail. Don't add level or temperature loops until strategic loops are defined. Use simulation continuously. Validate controllability as loops are added. Adjust process if required. Collaborate across functions. Align control priorities with operations, safety, and economic objectives. Modern integration. The hierarchical procedure aligns well with today's design and operation environments. Digital engineering platforms enable real-time synchronization between PFD, P&ID development, and control strategy mapping. Cloud-based collaboration allows simultaneous input from control engineers, process designers, and operations teams. Modular automation. Each control level can be digitally validated and deployed independently or as part of larger orchestration schemes. Summary. The hierarchical procedure brings structure, clarity, and foresight to control system design. By layering control complexity in parallel with process development, it prevents oversights, reduces rework, and ensures that strategic, tactical, and regulatory control objectives are embedded into the plant from the earliest stages. In the digital era, this methodology is the foundation for intelligent, adaptable, and future-ready process automation.